In this lesson, we're going to finish applying the rational root theorem, and we're going to tie in the fundamental theorem of algebra. In the previous lesson, we learned how to identify our p's and q's using the rational root theorem. So when I look for the p's and the q's, just to reiterate, this would be my factors of the constant term. So factors of 15 would be plus or minus 1, and 15, 3, and 5. Factors of q, the leading coefficient, would be the 6, so 1, 2, 3, and 6. But then René Descartes discovered it would be in the list of p divided by q. So if I take each of the p's and divide it by 1, I would get the same list. So 1, 3, 5, and 15. But then when I divide by 2, that's 1 half, 3 halves, 5 halves, 15 halves, and I'm nowhere near done. Then I got to divide by 3, so that's 1/3. 3 over 3 reduces to 1, 5 over 3, 15 over 3 reduces to 5, I already have that, but then I gotta divide by 6. So that'd be 1 6, 3 6 is 1 half, 5 6, and 15 over 6 reduces to 5 over 2. So there's my entire list. That's a lot of values, and I gotta check both the positives and negatives. So we can use technology to help us even further. If on your graphing calculator you actually graph this function, you're gonna get a curve that looks like this. So I can see right here that -3 is a 0. So if I have a starting point, that's gonna make my life so much easier. So since -3 I can see is one of my zeros, I can see it also crosses probably at a fractional value, but I'm going with -3 to start. I'm going to do my synthetic division using -3, pick off my coefficients 6, 25, 16, and -15, bring down the 6, multiply would be -18, add would be 7, multiply would be -21, add gives me -5, multiply gives me 15, I get a remainder of 0, which I knew I should get because -3 was one of my zeros. Okay, so from this point, this gives me a quadratic, and it potentially could be factored, but I'm not positive that it can, especially because I see that there are fractional, could be even irrational values, so quadratic formula is an option. But I'm going to check and see if it can be factored. So just for good notation, I'm going to show you what I have so far. So since my 0 was was -3, the factor's +3, x plus 3, times the remaining depressed polynomial would be 6x squared plus 7x minus 5. So I'm going to try to factor this remaining trinomial here, and I'm going to do that using tic-tac-toe off on the side. So factors of 6x squared, I'm going to start with 2x and 3x. Possibly could be 6 and 1 if this doesn't work. And I need factors of -5. So one of them needs to be negative and the other needs to be positive. I'm going to try 5 because that'll give me -10 and +1. Oh, I can tell already I have a small thing that's not going to work, so I'm going to change my signs to this one positive and this one negative. So as I go across, that's 10x and -3x adds to 7x. So my one factor is 2x minus 1. My other is 3x plus 5. And I have this x plus 3. So I am going to apply the zero product property. So my first one would be x plus 3 equals 0, gives me a solution of x equals -3. Then I have 2x minus 1 equals 0. So this would be 2x equals 1, divided by 2 gives me x equals 1/2. Notice that was in my original list. So is -3. And then I would have 3x plus 5 equals 0. 3x plus 5 equals 0. Subtract 5 from each side gives me 3x equals -5. Divide by 3 and I get x equals -5/3. So that was in my original list as well. So if you have rational zeros, they're guaranteed to be in that list. If they're irrational, of course, it won't be captured by that list. All right, this brings me to the fundamental theorem of algebra. A function will have the same number of zeros, they could be real and complex, as the degree. So what's that mean? That means if I have a function that's to the third power, third degree, it has to go through the x-axis 3 times if they're all real. Now, it is possible that it'll be something like this, where we only physically see it go through one time and the other two would be complex. So it must always have 3 solutions or 3 zeros. So we're going to use this idea to find all the zeros of this quintic function. So how many zeros does it have to have? It has to have 5. So I'm getting a starting point here. As I look at the graph, yeah, I could list all my P's and Q's, but I know for sure right there it's hitting at -1. I also see over here that it's hitting or crossing through at +2. We'll talk about the difference there. But what am I going to do then? I'm going to do synthetic, and I'm probably going to do it more than one time because this is to the 5th power. So I'm going to begin using, remember it's always the 0 that goes on the outside. I'm going to use -1. So I'm going to bring down the 1, multiply, add, go ahead, crank out your synthetic. And there I go, I got a remainder of 0. Now I'm going to do it with the other 0 that I see. I see 2 is a 0, so go ahead, pause the video, check your answer when you're ready. A remainder of 0 again. Now, one of the things that's kind of interesting here is you see how this bounces off the x-axis? When that happens, I alluded to that before, that means that this 0 of -1 is there twice, okay? It has what we call multiplicity 2. So I'm going to do synthetic one more time using -1 again. And that's going to help me drop down my remaining polynomial down to a quadratic. All right, each time notice I'm getting a remainder of 0. If you don't, then you have used something that is not a 0, or you've made an error in your synthetic division. All right, so here's what remains. This would be x squared minus 4x and plus 7. Now, from the graph, I'm not going to try to find a rational 0 because I only physically see 3 zeros in the graph. I know that it has to have 5. So where are the other 2? Well, they're going to be complex. And they would come from the quadratic formula. So I'm going to quickly do the quadratic formula. So x equals -b would be 4 plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 7, all over 2 times a is 1, so all over 2. So I'm going to evaluate the value of the discriminant. So my discriminant is -12 over 2. So definitely my discriminant's negative. I'm going to have a complex solution involving I. So if I break down -12, that would be -1 times 12. That breaks into 4 times 3, 2 times 2. We've done this so many times this year. Hopefully you're picking up your speed. So this would be 4 plus or minus 2, because I have a pair of 2's, I root 3 all over 2. If you could clean it up just a little bit more, we would have x equals 2, because I can divide by 2 here and 2 here, plus or minus 1i root 3. There's 2 answers. What are my other ones? I'm just going to bring them down here. -1, +2, and I have -1 a second time. So there's a total of 5 zeros, which matches the fact that it is a 5th degree polynomial. So here's a summary of what I just stated. If the 0 repeats itself an odd number of times, it cuts through the x-axis. Okay, so your graph, your curve is gonna, like if it's just gonna go right through it. Whereas if it's there an even amount of times, like you have x plus 2 to the 2nd power, that means at -2, where the 0 is, it's going to bounce off the graph, won't cut through. All right, so we're going to do a summary of everything we learned here. First thing I'd like you to do is, of course, read the directions, which are telling us to find all the zeros. And you're told you can use your calculator to possibly help you here. So if I list my P's and Q's, my factors of P would be 1, 2, 4, and 8. My factors of Q are 1, so P divided by Q is going to be this list and its opposites. So if it has a rational 0, it will be there. Now what I'm going to do is I'm going to throw this in my graphing calculator. I'm going to hit y equals, and I'm going to look at the image. So when I see my graph, I can see that it's cutting through here at -2 and it's also cutting through at +1. Okay, so I'm going to totally use this graph to help me get started. So I'm going to use -2 in my synthetic division. So pick off the coefficients 1, 1, 2, 4, and -8. Okay, go ahead, crank out your synthetic, bring down your 1, -2, add, I get 4, multiply, add would be 0. Good thing, it's supposed to be. All right, so I'm going to do synthetic again with that remaining depressed polynomial. I'm going to put 1 on the outside and repeat my synthetic. Get a remainder of 0. All right, so I can physically see 2 of my zeros. The other 2 must be complex. So how am I going to get them? Well, they're going to come from this depressed polynomial. Just to show you what I have so far, my factors would be x plus 2, x minus 1, notice it's opposite of the 0, times, here's what I have left, x squared plus 0x, so I'm just going to put plus 4. Plus or minus out front. Square root of -4 would be 2i. So it's positive and -2i. There's 2 solutions. My other 2 are -2 and x equals +1 for a total of 4 solutions. It matches the degree. I'm in good shape. This last one, I would like you to do it completely and then check your solution. So when I look at the graph in my calculator, I see zeros at x equals -3 and -1. Okay? So I'm going to do synthetic with these values. When I do it with -3, I get a remainder of 0. I'm going to do it again with my other 0 of -1. And what does this leave me with? I have f of x equals, my factors would have been x plus 3 and x plus 1 since I can see the zeros. And this would be x squared plus 4 remaining. So this is very similar to that last one. So my 3 zeros would be -3, -1, and I just did this 2 seconds ago. It was plus or minus 2i. Rewind the video if you need to see that one again. There's a total of 4 solutions. It's quartic, so by the fundamental theorem of algebra, I've got them all.